Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. On this occasion, allow me to introduce myself. I am Humaira Salsabila from Universitas Syakuala Aceh, Indonesia, and I will be presenting the result of my research about application of the alternating direction implicit or ADI to the full potential equations. The first, introductions. In modern computational aerodynamics, a key challenge is obtaining accurate and stable numerical solution for fluid flow phenomena modeled by partial differential equations (PDE). The nonlinear full potential, widely used for inviscid and irrotational flow, requires efficient numerical methods, and the alternating direction implicit or ADI methods offer an effective solution by splitting and a problem into alternating one-dimensional steps. This approach enhances stability, accuracy, and computational efficiency, making ADI a strong framework for solving the full potential equations. The next is partial differential equations, an equation that involves derivative of one or more dependent variable with respect to more than one independent variable. For example, we can see in first equations where the function u, which is the dependent variable, has two independent variables, namely x and y. The general form of a PDE is as follows: two equations. The general form of a first-order PDE we can see in third equations, and general form of second-order PDE we can see in fourth equations, where u equal uxy is unknown function and the coefficient a, b, c, d, e, f, and g are function of x and y. From the general form for equations, PDE can be classified into three types of equation based on the value of the discriminant, where a, b, and c is coefficient of the quadratic equations. We can call elliptic if d less than null, if parabolic if d equal null, and the last is hyperbolic if d greater than null. A PDE is said to be linear if the unknown function u and all of its derivatives appear only the first power, the function u and its derivatives do not multiply each other, and there are no non-linear functions of u or its derivative in the equations. The general form of AND or the linear PDE as follows: 9 equations, or in operator form we can see in 10 equations, where L is a linear differential operator. One of a nonlinear PDE in fluid dynamics is the full potential equation. The next is finite difference methods. This method derives the formula by performing discretization using the Taylor series. This method transforming the domain of the independent variables into the finite grid, or what is called a mesh, after it has been approximated. The Taylor series around x equal x0 is as follows: 11 equations. Next is finite difference approximation for the first derivative. Let ux be a continuous and differentiable function. The first derivative u accent x can be approximated using several finite differential schemes. The first one is forward difference, the second one is backward difference, and the last one is central difference. The next is finite difference approximate for the second derivative. The second derivative u double accent x can be approximated using the central difference schemes. We can see in the from 15 until the 17 equations. The presence of these two conditions will produce a numerical solution that approaches stability, that is initial condition and boundary conditions. The boundary conditions can be classified into three types. The first one is Dirichlet boundary conditions. The second one is Newman boundary conditions, and the last one is Robin boundary conditions. And the next method is explicit method. This method using the current solution values to directly compute the next solution values at each grid point without the need to solve a system of linear equations. This method using the forward difference approximation for the time derivative and the central difference for the second spatial derivative. For example, in the equation 7 as follow 18 equations, let's Rx and Ry, then equations 17 become like in equation 19. Now, this method is stable if Rx plus Ry um, less than or equal a half. The next is implicit method. This method computing the next solution values by solving a system of linear equations and using the backward difference approximation for the time derivative and the central difference for the second spatial derivative. In the same manner as explicit method, then the implicit method for the equation 7 is given as follow 20 equations. The method applied in this research is the AD or alternating direction implicit method. This AD, the first developed in the 1950 by Douglas and Radford as well as Pisman and Radford. The ADI method consists of two solution stages at each time interval. The first step is the solution is computed implicitly in the x direction and explicitly in the y direction, resulting in a half time value. And in the second stage, the directions are reversed, where the y direction is solved implicitly and x direction explicitly to obtain the solution at the next time level. The solution is known as plate time stepping. For a grid in which t is taken as the independent variable, the resulting three-dimensional grid can be visualized as follows. For the step 1 of ADI, we can see the time derivative of time and derivative of dimensional x and y, then become the equation 24. Like in the slide, we can see that from the equation 24 can be the equation 25. In the same way, the second half the time we can see in the 26 and we get the equation 27. Based on 22 and 24, the general form of ADI can see in the equation 28 and 29. A tridiagonal metric is a metric whose non-zero entries appear only on the main diagonal and upper subdiagonal and the lower subdiagonal. Because the resulting matrices are tridiagonal, the next step is solve them using the Thomas algorithm, which is an efficient method for solving tridiagonal linear systems. The methods consist of two steps: forward elimination and backward substitution. Forward eliminations we can see in the equation 30 and backward substitution we can see in the 31. The next is about chapter discuss and result. In this research, we can see that full potential equation is used to model fluid flow that is inviscid, irrotational, and fully compressible. The two-dimensional full potential or FP equation for compressible, inviscid, irrotational flow is given by equation 32, where the density rho is related to the velocity potential V through the energy equations. We can see in the 33. where m is match number and gamma is ratio of specific heads. This is a nonlinear that is elliptic in subsonic region and hyperbolic in supersonic regions. For the step of method ADI, the first one is linearization of FP equation, that is using an iterative approach, which is the first one is use row n from the previous iterations, and the last one is solve a linear PDE for Pn plus 1. We can see in the equations 32, after obtaining Vn plus 1, update the density using the energy equations. The second step is ADI discretizations. The step 1, we choose the X implicit. We can see in the equation 33. And the second step is we choose the Y implicit, and we can see in the 34 equation 34. Each half steps produce a tridiagonal linear system that is solved efficiently for each row x direction or column y directions. The third step is tridiagonal system. For the x implicit half step, the system for each row is A, C, G, and plus a half equal B, where the matrix A is tridiagonal. We can see the matrix A in the slide, and there are my references. I think this is an overview of my research. That is all I can share for now. I hope that my research will be useful and can be applied in the future. And the last I say, wassalamualaikum warahmatullahi wabarakatuh.